Artificial intelligence has quietly moved into mainstream CAD software, making its way onto the mechanical engineer's workstation to alter how parts are initially shaped. Instead of drafting a single geometry line by line, engineers now use generative design. They input the physical limits, define the materials, and set the load cases, the specific maximum forces the part must survive. The software then generates vast families of candidate shapes. To find the most efficient structural form, the algorithm performs a process called topology optimization. It calculates the internal stress pathways and mathematically strips away any non-load-bearing mass, leaving behind a highly efficient skeletal structure. Historically, arriving at an optimized design like this required weeks of manual trial and error. That hand iteration process has now compressed down to just a few hours of background computational processing. But all that computing power doesn't yield a finished product. A human engineer still has to sit at the monitor, scroll through the grid of generated options, dismiss the unviable geometries, and select the few that are actually worth manufacturing. The generative software cannot invent. It calculates possibilities, but only inside the strict physical constraints defined by a human expert's domain knowledge. Once a geometry is selected, engineers need to validate how it will handle real-world conditions. Algorithms are also stepping in here, accelerating early estimates for fluid flow and physical stress before any metal is cut. This visualization shows a machine learning surrogate model in action. Trained on past simulation datasets, they instantly output predictive thermal maps, bypassing hours of rigorous solving. But there's a risk. They are completely blind to physical reality if the underlying inputs are flawed. If an engineer leaves out a crucial load case or sets an unrealistic boundary condition, like ignoring how a part attaches to the machine, the AI will return a result that is confidently wrong. Recognizing a false positive requires physical intuition that the code lacks. This computational speed creates a new vulnerability. Because the software generates answers so quickly, the human engineer's ability to cross-check digital outputs against physical reality is more vital now than ever. Moving past individual components, a complete mechanical design involves integrating multiple subsystems and coordinating with complex supply chains. This requires constant human negotiation and rigorous in-person design reviews. Digital estimates inevitably have to face real-world physics. That means taking the agreed-upon design and building a physical prototype for hands-on validation. Out in the test lab, there are no shortcuts. When a hydraulic actuator drives down onto a part, the applied physical forces quickly expose the microfractures and stress points that digital models missed. Engineers do use language models to draft post-processing scripts, automate parameter sweeps, and format final test reports. But the final authorization on those reports cannot be automated. In regulated fields like aerospace or medical devices, failure investigation and legal liability fall squarely on the professional engineer. That final physical sign-off remains a strict, uncrossable boundary for AI. With standard calculations, routine drafting, and documentation being absorbed by algorithms, engineering teams are naturally questioning how the workforce will fare over the next decade. This chart compares expected employment growth through the year 2034. It shows that demand for mechanical engineers is projected to increase, outpacing the average growth rate across all other occupations. The clearest shift falls on the beginning of the career path. Automation compresses the traditional entry-level experience, meaning junior engineers no longer start by performing basic drafting tasks or manual calculations. Instead, modern entry-level roles have evolved. Junior engineers are immediately tasked with managing AI tools, scripting workflows, and evaluating complex generative outputs. With tools handling routine calculations early on, hands-on mentorship is more important now than ever. Senior engineers have to stand at the workbench and physically show their early career staff what the algorithms failed to predict in real-world materials. To see how top engineering teams train staff to operate these tools and manage the modern workflow, explore the resources linked on our platform. Artificial intelligence does not remove the need for mechanical engineers. It forces an evolution, elevating human professionals out of the drafting routine so they can serve as the ultimate judges of computational power.